Even though fusion is something that we would like to do, it's not practical yet. The sun laughs at us every day as it quietly goes about doing fusion without any of the mechanisms we have to try to put in place. It turns out, though, that it is easier to create energy by breaking down heavy nuclei using fission. We said the iron was the most stable thing, and we see that these are less stable. So if we have a very heavy nucleus, we can break it apart and we can take that mass deficit and turn it into energy. Not as much energy as we could do over here, but it's easier. We've figured out how to do that. So we have it splitting into two lighter nuclei. And when it does that, it will generally release neutrons and or energy. And of course, we'd like the energy. It turns out that uranium-235 has several different types of fission reactions. And in each case, the sum of the masses of those products is less than the uranium-235 and the neutron that started the whole business. And that mass can be converted to energy. This is what is happening within the whole cycle. You have uranium-235, and if you hit it with a neutron, it will become uranium-238, which is very unstable and falls apart. Here's a typical set of things that might come out of a fission reaction. Barium and krypton and a whole bunch of neutrons. Oh, it only needed one neutron to start, and here this one is emitting 3. If one of those goes on to hit another uranium-235, turning it into yet another uranium-236, it turns out there's other possibilities that could happen, but again, it's going to release neutrons. We aren't bothering to tell you what all the other possibilities are, but you can come up with. They usually come as fairly equal. This one, the 141 mass, is quite a bit more than a 92 mass, but they tend to be fairly equal in their distributions. And each time, though, you're going to get more neutrons, which can proceed to find another one of the uranium-235s to hit and start another fission event. And that is what is happening as far as a chain reaction. Now, we know these things aren't tightly put together even when because the nucleus is so much smaller than the whole atom. So you have to have a certain amount of this uranium in there before this would ever become a chain reaction and keep going. This number is called critical mass. You've got to have a certain amount of the stuff that will fall apart in order to maintain that chain reaction. It turns out if you want to do a nuclear reactor, it's between 3 and 4% of your material needs to be the uranium-235. Now, if you're not interested in making power on a sustained basis, if you want to just blow it up, you're going to need 85% of the uranium-235 in order to have it blow up instead of just sort of fizzling and blowing itself apart and just making a mess. Meanwhile, here we have our nuclear reactor. This is a generalized idea of what's going on. This area is the reactor core, and we have within it the uranium is in the fuel rods, and then you have what are called these control rods that keep it going at a nice moderate pace. We don't want it to go kapoo. Not that it really can go kapoo, but it can melt down. All right, and we have a pump here that is circulating either water or liquid sodium. It comes in cool, and as it goes through here, it's picking up all the heat that is being given off in the nuclear reaction. So when it gets up here, it is as hot as it could possibly get, right? And then it's taken over to an area that's full of water, and it transfers that heat to the water, which makes steam. And then you go into the idea that any steam engine can create electricity. It's going to create some sort of power. You're going to use this steam to power a turbine and take some electric power out of it. It's still going to be pretty hot on the other end. So you're going to have to cool it down some more so that it's cold again so that it's water again, so it can pick up the heat over here. So you're going to have either you're going to see cooling towers or whatever in order to get rid of that extra heat. Because if we were trying to get more energy out of it, it turns out to be less efficient to do that than to simply cool it down and get on with it. So these nuclear power plants will have the fuel rods that are enriched to 3 to 4% of the uranium-235, because uranium has many different isotopes, and the uranium-235 that is used is not normally at 3 to 4% in any situation that you might find in nature. You end up having to purify it. And the control rods, which are generally made out of either boron or cadmium. What are the control rods doing? Well, they're there so that if need be, they can absorb neutrons. If they do that, they absorb the neutrons, and neutrons are not able to continue the chain reaction. So that's how you shut it down. And that pressurized water is around both the fuel and the control rods. And the water is just transferring the heat to the generator. And the water is also a moderator. It will absorb neutrons as well, but not as effectively as those control rods. In a breeder reactor, you have a rather interesting situation where you can have the fissionable material that's produced can also be used as the fuel. So it is literally making more of its own fuel. That's a very interesting thing to contemplate. But because we're just taking the smallest little bit of the energy, because of its being from the mass deficit, it turns out that this is a practical thing that one can do. Now, here we say, I told you that it doesn't normally come at 3 to 4%. It turns out, even though it is fissionable, and it's the most abundant fissionable isotope, it's still only 0.72%, less than 1% of the uranium in uranium ore. So in order to enrich it to those percentages that you need for reactors, you have to use centrifuge systems, and they have to spin it. You know, a centrifuge is separating heavier things from lighter things. And here you are, you're talking about two different isotopes of uranium. There's not a big difference between the weights, so you have to do these centrifuge systems for quite a long time in order to do the separation.